Prove that for any positive integer n raised to power 5 minus n is divisible by 30. So that is the question we want to prove. Let's check for some numbers before we generalize it. That is, n raised to power 5 minus n is divisible by 30. So let's check when n equals to 1. So put 1 here, 1 raised to power 5 minus 1 equals to 1 minus 1, which is 7. The 0 is divisible by 30, so this one is true. Then when n equals to 2, 2 raised to power 5 minus 2 equals to 32 minus 2. So we have 30. Then this is also true. Then when n equals to 3, n equals to 3, 3 raised to power 5 minus 3 equals to, now 3 raised to power 4 is 3 raised to power 4 times 3 minus 3. So we have, let's factorize 3 out. 3 raised to power 4 minus 1, then multiply by 3. So 3 raised to power 4, 3 by 3, 9, 9 by 9, we have 81. We have 81 minus 1, then multiply by 3, which is equals to 80. When we multiply by 3, we have 240. So 30 can go into 40, then this also true. Then we want to generalize it now. In generalizing the proof, now what are the prime factors of 30? 2 can go in 30 is a prime number, 3 can go in 30 is a prime number, 5 can also go in 30 is a prime number. Now we need to look for, using the knowledge of modular arithmetic, the congruence class that is 0, 1 in mode 2. Using the knowledge of modular arithmetic, 0, 1, 2 in mode 3. 0, 1, 2, 3, 4 in mode 5. So that is what we need to do in generalizing the proof. So this, we need to prove this, that is, in generalizing the proof now, we need to apply the method or the knowledge of modular arithmetic in generalizing the proof. Then we have n raised to power 5 minus n can be factorized as n is a common factor. We have n raised to power 4 minus 1. So which equals n into n raised to power 2 raised to power 2, then minus 1 raised to power 2. Using knowledge of difference of two squares, we have n into n squared minus 1, then n squared plus 1. So this can be factorized further. We have n into, this can factorize further as n minus 1, then n plus 1, then n squared plus 1. Now the next thing we are going to do, we are going to test whether when we substitute 0 into this, so whether the result will be 0, and when we substitute to 1, whether it will be 0 in mode 2. Then we have n into n minus 1, n plus 1, n squared plus 1. So we want to substitute when n equal to 0. So when n equals to 0, n equals to 0. So when n equals to 0, that is, we have this, when n equals to 0, we substitute. We have 0 for n, 0 minus 1, 0 plus 1, then 0 squared plus 1, then you are going to have 0 in mode 2. Mode 2. So therefore, so when the 0 is substituted here, then it means that this is divided by 2. Now let's check 1. Then when n equals to 1, so for wherever you see n, you put 1, then 1 minus 1, 0. So 1 minus 1, then in place of n we have 1 plus 1, then 1 squared plus 1, then equivalence to. Now when any number is multiplied by 0, you are going to have 0 mode 2. So we are able to prove that for this expression here, for any positive integer, it is divisible by 2, according to what we have done here, because the remainder is 0. And any number that leaves the remainder of 0 when divided by 2, it implies that the number is divisible by 2. So that is the implication. Now any number that leaves the remainder of 0 when divided by 2 means the number is divisible by 2. So we have just proved that this, for any positive integer, n is divisible by 2. So now we want to prove that it's divisible by 3. So we are going to substitute 0, then substituting 0 again, we have done it, we have this, then we substitute 2. So when n equals to 2, we have 2, that is n equals to 2 minus 1, 2 plus 1, then we have 2 raised to power 2 plus 1, which is equals to, this is equals to 2 into 1, 3. Then we have 2 raised to power 2, 4 plus 1, 5. Then which is equivalent to 0 in mode 3, because 3 can go. When you divide the result of this number by 3, the remainder will be 0 in mode 3. Now the next thing, so we are able to prove for 0, 1, 1, 0, 1, 0, 1, 2. Then because the remainder here is 0, implies that when you divide it by 5, the remainder will also be 0. So that is the implication here. Because we have 0 here when divided by 2. And also that means we have test for 1, 0, 1. Because 0 and 1 is also a congruent class of 5. Then we have be able to test for 2, which is also a congruent. Then we need to test for 2. So here we have to test for 2. Then using mode 5. Then when you substitute for in mode 5, we are going to obtain the same result in mode 5. We have 2 by 1 by 3 by 3 by 5 equivalent to. Now when we divide the result, because 5 is one of the factors, so we are going to have 0 mode 5 to mode 5. So that's the implication here. So the next thing is we are going to check for 3. So because 3 is also a congruent class in mode 5, so we have n equals to 3. 3 for n, then 3 minus 1 into 3 plus 1, then 3 square. We have this 3 square plus 1, so which will give 3 by 2, 3 plus 1, 4, then 3 square, 9 plus 1, we have 10. So because 10 is one of the factors here, so when you divide 10 by 5, the remainder is 0. Multiply 0 with any number, you are going to have 0. That is 0 mode 5. Then it shows that 5 can also go. So we want to test for 4 now. N equals to 4. So in place of n, you put 4 there. 4 into 4 minus 1. 4 plus 1. Then 4 squared plus 1. Then we have 4. Then 4 minus 1, we have 3. 4 plus 1, we have 5. Then 4 squared, we have 16 plus 1, 17. So now, since 5 is one of the factors, and when 5 is divided by 5, the remainder is 0. Multiply 0 with any number, you are going to have 0. Is 0 mode 5. So that shows that from what we have done now, so we have 30 can go in n raised to power 5 minus n for any positive integer, for any positive integer n. That is, we have n belongs to the positive integer. So that is the final answer for the question we are able to prove here. So we are able to establish a proof that for any positive integer n raised to power 5 minus n is divisible by 30, with what we have just done here now. Thank you. Please like, comment, and subscribe to our YouTube channel for more educational content. If you have any question, you can drop your question in the comment section. Thank you.